Okay, everyone, welcome back. And I guess I'll just tell you what I decided here. I decided that, you know, at this point for the insertion stuff, you guys could probably use the flasher, figure out where switches are, and everything like that. You can get the post insertion config ready, and that stuff will be fairly obvious. So here I'll be taking the sort of deeper dive in for the next parts with, like caution warning operational check. So we're starting here with the caution warning operational check, and I could talk about the system a little bit. So we'll make a save real quick, just because I'm going to be, doing some talking, so we best have a save. We'll jump into it. So starting off with the caution warning operational check, the first thing we're going to do is we're going to hold shift click on lamp test, and you can see all 14 of these lights come on, and then we also make sure that the master alarm push button light is on. And it should only be on for the left side. That's good. Now we'll take it to test 2. Shift click. And again, it's out on the left side, out on the bottom. Master alarm light is on the right side. We've got our 14-ish lights here, or actually I think these are 20 lights. The left 14 caution warning go out, the 20 caution warnings on the right turn on. And then we just release the lamp test switch. And then we'll take caution warning from CSM to command module. And what this will do is it'll sort of turn off any lamps that are related to the service module and only allow those related to what's in the command module to turn on, as you can see here. We did get the master alarm tone, which will trigger for all of the positions, and that's just because we haven't pressurized our command module RCS. So there is something to talk about here. I just want to bring this up, that when on boost, you can see the light here on the left side doesn't turn on. The push button still works. The reason this light doesn't turn on is because it's actually the same color as the abort light. So during the launch, we didn't want, or they rather didn't want the astronaut to just see red and then abort, right? Because that's a very, natural human response to this type of situation. So that's why they put the boost mode in. And I'd also like to talk about the ACK mode. You can see on ACK those lights turn off. You still get the master alarm when an alarm condition is met. You can still ACK it like that, but notice when we push that, those lights actually turn on. They're slightly dimmer than what they would be on boost, and I could show that off. Or, well, they're supposed to be anyways. But you can see that when we hold it down, we do see the lights that are currently in the alarm state. And this is just a way of saving power with the caution and warning system. You'd be surprised at how much, you start getting a lot of these lamps, you'd be surprised at how much power that could take. That's a good way of saving power. And so that's sort of the in-depth look at all these switches. Caution and warning system, when its power is set to off, you can see. Same thing on the acknowledge mode. It's the master alarm light that goes dimmer, not the lights up here. My bad. You can see this still works. No alarm tone. We do get the master alarm light on for that caution and warning status, and that just tells us the power is off. We've got a backup power mode. All the same functions. Everything's the same there. And so if you want to turn off the caution and warning completely, then the only way then would be to untie it from both the main bus A and the main bus B, and we can see that completely takes that system offline. So that's sort of the in-depth dive into the caution and warning system and how it's operated. I'll go through the lights now. These
Apollo 7 Houston, you have about 2 minutes to LOS, and your Saturn tanks look perfectly nominal.
I can pause from here now. No reason for me to be unpaused. These BMEG temperature lights, 1 and 2, respond to our body-mounted attitude gyros, 1 and 2. Here we've got 2 independent ones. Temperature. So if the temperature gets too low, too high, excuse me, these lights will turn on. We'll talk about what these are later. The CO2, partial pressure high, that light will come on when this reaches near the yellow zone. That's the partial pressure of CO2 within the cabin. When it starts getting to a dangerous amount, that light will turn on. Problems with the pitch and yaw gimbals on Group 1 and Group 2 are dedicated for these lights respectively. Cryopressure, when the pressure exceeds the green zone or falls too far below the green zone on either H2 or O2. Glycol temp low. Glycol's part of the cooling system. If for whatever reason the spacecraft's not making a lot of heat, we've got evaporators running, radiators going, glycol temp could get low, and that light will come on. Command module RCS 1 and 2, those are rings, ring 1 and ring 2, and those are the thrusters located on the return vehicle, the command module, and the 4 service module RCS thruster switches or lights responding to group A, B, C, and D. These can come on for low pressure, low and high temperatures. A lot of stuff can bring this on, so it'd be up to you to sort of monitor the gauges at that point. We've got the SPS flange temp high. That'll come on if you've accidentally left like the SPS line heater on. After a while, the heat will communicate through the system and it'll hit the flange, and then that'll start making the temp high. That light will come on, just telling you, hey, turn the heaters off. Fuel cells 1, 2, and 3. Trouble lights, these correspond to the fuel cells of the spacecraft. Again, same thing with the RCS. A lot of stuff can set that off, so it'd be up to you to make sure if it's a temperature, a flow issue, potentially pH imbalance, cooling with the pumps. Pumps can get to the point where the fuel cell may still be sort of in the greens, but it'll trigger that light, high flow, low flow, that sort of stuff. So again, one of those multifunction lights that you have to go and manually inspect the trouble condition for that. And then we have AC bus 1 and 2. These will come on if the AC buses are tripped offline or undervolted. And they go to each respective bus. There are 2 AC buses. The fuel cell bus disconnect. When a fuel cell bus, each fuel cell is technically its own bus, just like each battery. When a fuel cell bus is basically untied from a main bus, you'll get the fuel cell bus disconnect light. Flipping the switches might not trigger that, but any automated disconnect will trigger that. AC bus 1 and AC bus 2 overload. So yeah, inverters, we get inverters for AC power since fuel cells are like chemically reactive batteries. So we get a function generator that generates AC power in 3 phases. There are 3 of them. 1 is redundant, 2 are online for bus 1 and bus 2. You can use one inverter on both buses, but it's not the recommended mode of operation. The AC will maintain stable voltage up until a certain point, and that's accomplished through yeah, what was it called again? I can't remember. It's phase width modulation. Yep, it's accomplished with phase width modulation. So as the amps go up, you keep the voltage stable. And the reason for that is because the phase and everything needs to be stabilized. The output in inverters needs to have a stable voltage for things to work properly. So as you put load on the bus, the inverter's signal to go up and down, on and off signal, basically rapidly pulsing, that that will change in width. And as you get to a certain point, the current will begin to rise and you'll hit the maximum amount that the phase width modulation can tolerate. And then what happens is, instead of raising your apparent power, which is measured in volt amperes, unlike DC power where you just multiply volts and amps and you get the watts, you can't do that on AC, because with the phase shift slightly being off, or with modulation, it could actually affect the output wattage, and you don't really know what it is, even with the volts and amps. So you multiply the volts and the amps, and you get not watts, but you get volt amperes, and that's your apparent power. That's how much we assume is going through. And when the amps rise, you get to the point where the inverter can't keep up and the voltage begins to drop. And that's the point in which the overload will kick in. You've got your command module computer light. This light can come on for a couple of different reasons, most common being the command module computer going into standby or completely powering off. Your crew alert light, this is something that can come in through real-time commands through your up data link. Or uplink telemetry, and that'll set a relay that turns that light on as just a way to get the crew's attention. Then you've got your main bus A and B undervolt. So again, unlike AC, which wants that stable voltage up until it can't, well, at least on inverter outputs, on DC, their actual power, it's not apparent power, it's actual legitimate power and work measured. So as you increase the amps, you will proportionally decrease the volts. So if you put too much load on a bus, the volt drops and you get an undervolt issue, and you can get these lights flickering, power, going crazy, because you need both the right voltage and amperage to run powered pieces of equipment. Another common cause of an undervolt is just not enough power being supplied by the fuel cells. Fuel cells are taken offline, and in that situation, you don't have enough of either volts, or both volts and amps. So that's another thing. And those go to bus A and B respectively. Again, two main buses, sort of redundant, but also slightly not. In its standard configuration, if you lose main bus B, you'll have this whole bottom section blackout. And you can switch all that to main bus A, but that will black out. And then main bus A going offline will black out this entire upper section of everything that uses the DC. But super important stuff. For example, we see pilot valves on the engine, the computer cross-tied on both main buses. So if you lose one main bus, you still got power on the second one. So that's our form of redundancy here. The next is the inertial subsystem, ISS. This is basically our inertial measurement unit, our IMU coupling data unit, as well as, I believe, the nope, OSS specific lights, I think are down here, optical subsystem. So there's optical coupling data unit. This one's paying attention to the IMU coupling data unit. And so any flaws in that will cause the ISS light to go on. Most common cause is turning off the IMU. I don't even think that going into gimbal lock would cause that light to turn on, since it just enters in align mode, which is a standard mode of operation. Like, you don't want that light to go on every time that you do a course align by changing your refs mat. And we'll talk about that later and what those words mean. But you know, there are certain times where you'll enter in align mode or no attitude light comes on, and you don't want the alarm to go off for that. So most common cause is switching off your IMU. But there are other causes that will have the inertial subsystem light go off. For example, jet on monitor program, part of the Artemis ropes, and I believe, or maybe, excuse me, not Artemis, Skylark ropes. The jet on monitor, that'll cause that light to go on. Again, we've already talked about the caution and warning system light. O2 flow high, any high flow of oxygen. Basically, when this O2 flow gauge exceeds 1, that light will trip on after a couple seconds. And the soot compressor light. Soot compressor light will turn on when the compressor either can't keep up and there's too much differential pressure between the compressor and the cabin, or if it's over pressurized and the cabin is too below it and it needs to bleed off and it can't do it fast enough. So basically just a high delta pressure is your most common cause for that. In normal operation, you're probably pressurizing the cabin. After, you know, you're pressurizing the lunar module and you're depressurizing the cabin, and then you go and you start repressurizing the cabin with the repress package up there, and the soot compressor can't, you know, keep up with the rate of oxygen that's being dumped in. That's the most common cause for that. An O2 flow highlight, most common cause for that is pulling the soot circuit return or pushing it back in. Starts a purge sequence on the soot loop, and as well as any cabin pressurization cycles, since there's always a small bit of leakage of the pressure, and over time the system will automatically pressurize the cabin. And anytime that cycle comes up, you can get the high O2 flow light coming on as well. So that's all of the light explanations and everything that can go on there, with a little bit of touch into some other systems, but we'll talk about those other systems in finer detail when we get to them. Closing out this checklist then. And I'll see you all in the next one.